Welcome back to Bazai. Today's quick tour covers GraphQL from a single service setup to an enterprise-scale federated graph. The core idea: clients declare exactly the data they need, and the server resolves it across backends, databases, REST services, and third-party APIs, with one endpoint and a strongly typed schema. Basic GraphQL architecture. A client sends a query to a GraphQL server. The server has type definitions that describe the schema, objects, fields, and relationships, and resolver functions that know how to fetch each field. Resolvers might call a database for users, a REST API for orders, or both in a single request. The response matches the query shape, no underfetching or overfetching, and the client gets a predictable JSON tree. GraphQL as an aggregator. GraphQL can sit in front of heterogeneous systems, legacy services, modern microservices, and SaaS APIs. The GraphQL layer maps schema fields to those backends, stitches results, and enforces access control and caching policies. This aggregator pattern avoids API sprawl on the client, provides one auth model, and lets teams evolve backends independently while keeping the client contract stable. Federation: one graph, many teams. As organizations scale, a single GraphQL server becomes a bottleneck. Federation splits the graph into subgraphs, owned by different teams, while exposing a unified API. A GraphQL federated gateway composes subgraph schemas into one supergraph at runtime or build time, routing incoming queries to the right services. A schema registry stores versions, validates composition, and prevents breaking changes before they hit production. How subgraphs work. Each subgraph defines the types it owns, say, the user, entity in service A, and order in service B, and can extend types owned by others with new fields. Keys identify the same entity across services, enabling the gateway to join data, fetch the user core from service A, then resolve user.orders from service B, all in one client query. This preserves team autonomy while guaranteeing a consistent contract. Performance and reliability patterns. Data loader style batching. Collapse many field resolves into fewer back-end calls. Caching at field or query level with TTLs, E-tags, or persisted queries to cut payload size. Authorization in resolvers with scope checks, schema directives to annotate security and ownership. Observability. Trace resolvers, tracks slow fields and surface error paths to owners via the registry. Limits and cost analysis. Cap query depth/complexity to protect backends from expensive queries. If this helped, like and subscribe to Bazai, and share whether the next project needs a simple aggregator or full federation.